Hello folks, this is an update of my RPM counter or tachometer and balancing gauge to balance rotors and shafts that I've made 2 weeks ago. You can find in the description the links of the two videos about the making of the instrument and the other one about how I've tested it and the makeshift balancing rig used for testing. Today I show some improvements of the instrument and some insights that I've learned about balancing. One of the problems that I found was a certain instability of the angles calculated to locate the unbalancing mass. That was due because secondary vibration introduced by minor imbalances and noise caused by bearings. Those vibrations are picked up by the gradient pressure sensor, a piezoelectric disc sandwiched between two rigid plates, and are superimposed to the main oscillation caused by the main unbalanced mass. To avoid this problem, I implemented a moving average algorithm over the last 10 calculated angles to smooth off the noise. This worked great, and only when very noisy bearings are in use, as when I tested another motor that have something broken on one bearing making a clanking sound, still gives somewhat wandering numbers. However, as you can see in these images, the readout is quite stable. Also, I changed the time taken to count the number of revolutions to 10 seconds to have a finer resolution, and I added a series of progression dots to give some feedback to the user while the instrument is counting. Here you can see me while I'm measuring the quill speed of a drill press and the speed of a disc of an angle grinder. That, not surprisingly, featured a lower speed than the one stated in the specification label. Finally, I added a connector to convey externally the signals coming from the sensors and a data bus for future possible expansions. The most interesting thing, however, came with balancing again. Improving the makeshift balancing rig that I've made, I marked the exact location of the mass and compared with the pulses on the oscilloscope. Here the reference point, here where the screw is, here the maximum pressure. The finding was that, unlike what I've initially speculated, the unbalancing mass exerts its maximum pressure not when it passes over the sensor but lead it at 20 to 60 degrees. This seems to depend on the ratio of the whole rotor's mass and the unbalancing mass. However, I've not found a definite answer because the limited number of tests that I had the possibility to make. Transposed into a drawing, it appears that the reason of this should be the rotating mass is subject to a varying velocity because continuously changes its direction to follow a circular path. Therefore, we have a force that is tangent to the path circumference and a centrifugal force that makes the whole rotor generating the pressure wave that we detect with a sensor. However, the two forces combines and the result will likely be as the blue arrow in this representation, and when this vector is oriented toward the sensor, the maximum pressure will be detected, and the yellow arrow represents the intensity of the detector pressure. This is an approximate reconstruction of what should happen. However, I could have missed some points, and if you have suggestions, please leave them in the comment section below. Well, for today that's all folks. Thanks for watching, see you next time.